اتفضل يا دكتور.
Assalamu alaikum. Assalamu alaikum, everyone. Um, Today, هنتكلم إن شاء الله, we are going to talk about quantum computation. So, in the previous cases that we all saw in previous lectures, كنا بنعمل introductory part about quantum mechanics and how to treat a qubit. What's the difference between a qubit and the classical bit? How can we manufacture them or prepare them experimentally? فشوفنا systems كتيرة ممكن تشتغل كقubit. حاولنا نفهم quantum mechanics background of building a qubit. هنا today we are gonna talk more about quantum computation. So one of the very important things that we have to keep in mind is when we talk about quantum computing, it's very similar to what we used to do in classical computers. Basically, in classical computers, we have what we call it. If you think about it, you have electric circuits containing wires and logical gates. Okay, so when you design a classical computer, you need a circuit that has wires and logic gates, classical logic gates, of course. While when we talk about a quantum computer, we have to talk about wires and what we call it elementary quantum gates. So the quantum gates are the building units for a quantum computer. Using basically those quantum gates and those wires, we can manipulate the quantum information. If you guys remember, we talked last time, كلمنا آخر مرة على إنه الqubit in general can be written as your qubit. Okay. Can be written as alpha. Okay. I'm sorry. This is for the pen. Okay. So we said that basically the state of a qubit is made of a combination of, in the general state, of alpha 0 plus beta 1. And to make life easier, I can write that as alpha 0 plus alpha 1. Okay, so just use alphas for the coefficients. You can see that the state is a combination of 0 and 1 with 13 coefficients. And if you remember, so this is a single qubit. Let me explain that here. Okay, so as I said, this is a single qubit. Okay, and this is how it looks like. And then we said that we have to have what's called normalization. You need to remember this when we talk about a single qubit. So we said that alpha 0 squared plus alpha 1 squared has to be 1. And if you make a measurement on the qubit, you get a 0 or 1, and the probability is going to be alpha squared, alpha 0 squared, or alpha 1 squared. And if you talk about 2 qubits, and I'm repeating that here because we will use it now when we talk about what we are going to do next. So 2 qubits, what's going to happen when you have 2 qubits? Okay, it's going to be, in that case, as we mentioned, we will have 4 different choices for 2 qubits. This is why we did alpha 0, 0, and that was times 0, 0, plus alpha 0, 1 times 0, 1, plus alpha 1 0 times 1 0 plus alpha 1 1 times 1 1. So those are the different choices. If you have, you know, 2 qubits, you can store on them 0 0, 0 1, 1 0, 1 1. Okay? Are you guys following me? Everyone? So basically, this is how we do at the qubits. You can generalize that. So here we have 4 choices. What if I have 3 qubits? I'm gonna go to more than that. And then in that case, I'm gonna have 8 choices. هيبقى عندي 8 اختيارات، لأني لو عندي 3 qubits هيبقى عندي 8 اختيارات للثلاثة qubits، وبالتالي هيبقى عندي 8 ترمات في اليمين. As you increase things, the number of terms is going to be 2 to the power 2 to the power n. So that's the whole story. Okay, are you guys following me here? So this is how it looks like things. Now, one good way to play with qubits is that to represent a qubit as a column. كأني عندي عمود بتاع matrix بتاع مصفوفة يعني. فيبقى عندي هنا 0 1 ده بيمثل الابسايدي. فانا يعني انا البيزس بتاعتي هي 0 1، فهنا هكتب الفا او الفا 0 والفا 1 عشان امثل ابساي. زي ما انت شايف كده بنحط الكوفيشنتس بتاعت بتاعت الكيوبيت. فانا هحط هنا في المكان ده I'm gonna put basically الكوفيشنتس اللي هي this guy and this guy. So I'm gonna put here alpha 0 alpha 1. This is a good way to represent the qubit. So بدل ما نكتبها بالشكل ده، احنا نبقى عارفين لما نكتبها في شكل column بالشكل ده انه ده هو الكوفيشنت بتاع الزيرو وده هو الكوفيشنت بتاع ال1. طب how about so this was for Q1. If you call this Q1 وده هيسميه Q2 اللي هو ال 2 qubits يعني، فهيبقى المنظر بتاعه كالآتي. Q2 it's gonna be basically هيبقى عندي column okay made of 4 things this time طبعا. Okay, so this is how you represent ال qubits بتاعتك. ليه احنا عايزين نعمل كده؟ Because when you do quantum gates and you do quantum information processing, you have to represent your qubits على شكل مصفوفات أو على شكل أعمدة أو رو، هي صف يا عمود. لأنه هنشوف بعد كده الجيتس هتشتغل عليهم إزاي. ف this is what I wanted to start with actually to get you into the game, that we need to represent our qubits بالشكل ده. تبقى عمود فيه 2 elements زي ما انت شايف هنا، او لو كان عندي 2 qubits هيبقى عمود فيه 4 elements. طبعا لو عندي مثلا حاجة هي عددهم n qubits فهيبقى المنظر زي ما احنا متخيلين، هيبقى عندي هنا الفا 0 0 وهكذا ولغاية الفا مثلا 1 1 1 وهكذا، وعدد الاليمنتس دول هيكون عددهم 2 to the power n. فلو انا عندي n qubits this is how I'm gonna write الكيوب الستيت اللي بتمثل الكيوبيتس. تمام. Why do we need this? As I said احنا دلوقتي هنتكلم على السنجل كيوبيت جيتس. كويس؟ السنجل كيوبيت جيتس is very important for us of course, and if you think about it okay, this means أنا عندي 1 qubit وهعمل عليها operation، هعمل عليها process. في الكلاسيكال case surprisingly in the classical case the only non-trivial gate هي النوت gate which flips 0 to 1 أو 1 to 0. يعني لو أنت عندك classical gate على الكمبيوتر العادي، في عندي حاجة اسمها النوت gate. النوت gate what it does, it basically flips your bit. If it was 0, or if it is 0, it's going to be 1. If it's 1, going to be 0. Now, if you think about what is the corresponding gate in the quantum case, again, remember we have, let's say alpha, okay? Let's say we have alpha plus beta 1. If you want to flip it, لو عايزين نعمل flip للكيوبيت دي، محتاجين نعمل ايه؟ محتاجين ببساطة شديدة ان احنا نخلي الفا نخلي الفا تبقى هي اللي مضروبة في 1 وبيتا هي اللي مضروبة في 0. So this is how you flip it. I think someone has his mic. Okay, I'm gonna mute it. Okay. Okay, so as I said, احنا في الحالة العادية اللي هي في الكلاسيكال case, what we do is basically, okay, again, if you have here a 0, تعمل عليه not فيقلب يبقى 1. أو لو كان 1 هيقلب يبقى 0. Okay, this is what the NOT gate is gonna do classically. Now, in our case, we are talking about a qubit that is alpha 0 plus beta 1. So if you apply a gate like the NOT gate to this, what is it gonna do is basically flip them. So you get here beta, okay, 0 and alpha, okay, 1. So this is how you flip it in a quantum gate. As I mentioned before, this is very much if we use the representation as a column, اللي هو ان احنا نعبر عن الكيوبيت في شكل column. It's gonna be 0, 1, sorry, alpha, beta, coefficients, alpha وبيتا, وبعدين لما apply not عليهم, it should give me beta alpha. So this is how you do the NOT gate in the quantum case. So this is a quantum NOT gate. It's gonna flip your the coefficients of the 0 and 1. Now, one thing that we do when we actually, so it's gonna look hard to follow up things this way. So for that reason, we represent each gate in a matrix form. Okay, so the NOT gate can be written in a matrix form, and this is how it looks like. Why we represent it in a matrix form? Again, what we are doing here is very simple. You can think of it this way, that you simply are applying the NOT to the state, basically alpha 0 plus beta 1. And what you are gonna get at the end is basically beta 0 plus alpha 1. Sorry, the space here is not. Let me write this again in a better space. Okay. So what is gonna happen here is that, again, I'm gonna do it this way. You have the NOT gate, and it's gonna act on alpha 0 plus beta 1. And what you are gonna get at the other side is, this beta 0 plus alpha 1. So as you can see, I'm applying the NOT gate okay, to this qubit, and I'm gonna get a new qubit where it's flipped from the previous one. And instead of alpha 0 plus beta 1, you have beta 0 plus alpha 1. It's now, the thing is, you can write that in terms of the columns as I mentioned. So here, I'm gonna write this as alpha, beta. So here, I'm applying the knot to alpha, beta, and what you are gonna get is beta, alpha. Now, the good news is I can represent, since I'm representing the qubits as columns, I can represent the gate itself as a matrix. And since the column has a dimension of 2 times 1, basically, I can say that this has to be 2 by 2 matrix, okay? And in fact, that ends up in a very good way, because basically I can find what kind of matrix that can do the flipping. And as I said, it's going to be this matrix here, which we call it the X matrix. It flips your, so if you try now to use this, multiply this matrix times this column, خلينا نضرب الماتريكس دي times this column, and what's going to happen, it's going to flip, and you get this. Okay, يا جماعة? So alpha beta becomes beta alpha. So you are going to flip things by multiplying a matrix times alpha beta. Okay, everyone, are you guys following me? So, so as you can see, now we can represent the gates. The gate is the gate. Here we call it a single qubit gate. A single qubit gate because it acts on only one qubit. Okay, and that gate we can design it in the lab where you gave it. So it's like here, it's like a machine. It's like something that you feed it with the qubit, the original qubit, which is alpha 0 plus beta 1. And this is the X. And what it's going to give you out at the other side is beta 0 plus alpha 1. So as you can see, if you pass this qubit into the X, it's going to give you from the other side the flipped qubit. Okay? And we represent that in a matrix form, as we said, where you have a matrix acting on alpha and beta, and it's going to give you at the other side beta alpha. So this is the NOT gate. It's an example of many other gates. We can have many gates that are single qubit gates. Okay. Again, what is a single qubit gate? Why do we call it single qubit gate? Because this gate acts on one qubit. So it acts on one qubit, makes a change in the qubit, بتعمل تغيير فيها وتدينا qubit جديدة. Qubit في حالة جديدة, في state جديدة. So we start with our qubit in a certain state, نشغل الجيت عليها, تدينا القubit بس في state جديدة مختلفة. So this is the this is the NOT gate. Okay, this is the NOT gate. So this is what we have here. Very good. Is there other ones? Yeah, but before proceeding, okay, there is a very important thing, which is when we do such thing, remember we said that alpha squared plus beta squared, they have to be 1. So the thing is, what I'm gonna get from the other side has to satisfy the same condition. Okay? So
Doctor.
if yes.
Excuse me, Doctor. Everything is clear and we are following you. And this part has been explained before. So can we jump to the next topic, please?
Yeah. Okay.
Okay.
I
And
don't
then
know who
everything.
explained it. Okay. Okay. No problem. Good.
Thank you, doctor. Thank you.
Okay. So now what we are gonna do next is one of the very important things that we have to talk about is that you has to satisfy this. If you have any single qubit gate or any quantum gate, if you do, so we said, for instance, X is represented as we saw it before here as 0, 1, 1, 0. If you do the inverse of it, okay, we have to make sure that X times X is gonna give us 1. So unit matrix. So that's very, very important. Now, the thing is, what if we, okay, what if this is not satisfied? If this is not satisfied, the probability is not gonna be conserved. So one of the very important constraints on choosing a gate, that it has to have the unitarity property, which means if you multiply X by the inverse of itself, it's gonna give you the dagger, which is basically you take the transpose and the conjugate, you have to get basically the unit matrix. This is one of the important things that we have to impose on every quantum gates. Now there are more important gates like the Z gate, and we have also this gate leaves 0 unchanged and flips the sign of 1 to -1. So the Z gate takes you from alpha and beta, for instance, and gives you at the other side alpha and minus beta. Okay, so that's one thing about the Z gate. We have the Hadamard, which is a very famous one qubit gate. It's made of basically 1, 1, 1, -1, and this gate does a very interesting thing, which is that basically this gate takes, if you feed it with a 0, for instance, a 0 state, it's gonna create for you a 0 plus 1, okay, over square root of 2. So that's the Hadamard gate. Then we also can look at what happens to 1. If you feed the H, the Hadamard with 0, that's what you get. If you gave it 1, what you are gonna get is 0 minus 1, okay, over square root of 2. Okay, now so this is the Hadamard gate. It makes a linear combination. You are feeding it with a 0, but you end up with this or that. Good. One of the very important things that we would like to talk about also is that single qubit gates make rotations and reflections of you know, in the Bloch sphere. So basically, it's a kind of, you can think of it as doing a rotation because basically when you apply a gate, okay, to some guy like that, you are ending up with some new column, which means the direction of your vector, it might have been, for instance, here, but after applying the gate, you are now here. So it's a kind of making a series of rotations inside the Bloch sphere. Good. Some important, okay, single qubit gates, as we said, we have the X gate, the Z gate, we saw them already. As you can see, this flips beta and alpha, and this one gives you a minus sign, the Z, and the Hadamard basically takes 0 to a linear combination, and 1 also to a linear combination with a minus sign. So those are important single qubit gates. As I mentioned before, actually, you can represent basically your single qubit gate as a rotations around the x-axis, y-axis, and z-axis in your Bloch sphere. So this is the form that you might get here, that you may represent any single qubit gate. I'm not gonna go to the details of that, but basically look at this here. Any single qubit gate, this has to be, okay, I'm gonna write that here. This has to be basically unitary. So we have here a unitary matrix, and any unitary matrix can be represented this way. So you end up representing your qubit changes using this. Okay, the multi-qubit gates is basically are made of, okay, here in this side, we have the classical ones. So classical multiple qubit gates. Obviously, in this case, I'm gonna act with this guy, with the gate, on something that has 4 elements this time. So it's like, for instance, alpha 0, 0, alpha 0, 1, alpha 1, 0, and alpha 1, 1. So we are gonna act with this gate here on 2 or more qubits. So it means I'm gonna have 4 or 8 or 2 to the power n elements. Those are the classical, very usual, the very standard multiple qubits, which acts on 2 things. So here, if you feed it with A and B, that's A and B. We have A or B. This is another gate, which is the OR gate. This is the NOT gate. This is for single. But here, it takes 2 bits, as you can, 2 classical bits, as you can see, and gives me one answer at the end. Here it takes me again 2, and it gives, that's the XOR, and that's how we represent it. This is the symbol we use for it, and so on. So those are the kind of classical gates that we see. Here we are gonna talk about one that is the most famous quantum gate. So here is a 2 qubit gate, okay, that we are actually gonna talk about. It's, as I said, probably the most important and the most famous 2 qubit gate, which we called it controlled NOT. And this gate here receives 2 qubits, as you can see, A and B. And at the other side, you are gonna, in contrary to what we do in the classical qubits. So in the classical case, you know, I'm starting, as you know, with basically, sorry. In the classical case, I am starting with basically 2 classical bits, and I end only with 1 output. But here, as you can see, we start with 2 qubits, okay? So 2 states of 2 qubits, and I end up at the other side with 2 states as well. So in fact, that's different from what we have seen in the classical case. Basically, in the controlled NOT, you have an A, and you go to the other side with A. So A goes all the way to basically your to the other side. So you get the same A from the other side. But the difference here is the other qubit. So if you look at it here, you are starting, so we call that the control bit. And this one here is the target. And basically, when you look at A and B, and you apply a process, what this gate is gonna do, as I said, A goes all the way out. And here at the other side, I'm gonna get B XOR with A. So this is represented here. Actually, this is doing something similar to what happens in the classical gate. So if the control is 0 and the target is 0, you get 0 here. If 0 and 1, if this is 0 and this is 1, you get at the end here 1. If you have 1 and 0, you get 1, 1 and 1, you get 0. So basically, we end up in that guy having a value that depends on the combination of A and B. And so we start with 2 qubit states, and we end up with basically also 2 qubit states. The first is the same as A, but the other one is XOR. So that's an interesting one. Again, if you think of it, if you feed it with 0, 0, you end up having at the other side 0, 0. So your C naught basically gives you, if you give 0, 0, you end up with 0, 0. If you give it 0, 1, applying the rules that we have just seen, you get at the other side 0, 1, and so on. So each one that you are gonna give, it's gonna give you a different answer depending on what you have done or fed it with. Good. We noticed that the C naught can be regarded as a type of generalized XOR gate. The thing is, can we do that with other classical gates? The answer is no. Why? Because they are not unitary. Remember, we said any gate has to be unitary, which means you have U times U dagger is gonna give you 1. Again, U and U dagger are matrices, by the way. And basically, U dagger is U when you take the transpose and the complex conjugate. So this is how you produce U dagger from U. And if you multiply them, they should give you. So this is very essential in quantum mechanics because of the reversibility. You have to be able, if you, for instance, apply the X here and you gave it alpha, okay, let's say you give it alpha and beta, and it gives you beta and alpha at the other side, you should be able to reverse X to go from beta alpha to alpha beta back. So you have to have this possibility open for you. So basically, I should be able to go back. If I start with this guy, I should be able to make an X dagger and go back to alpha beta. So reversibility is very important. So the other classical gates do not satisfy that reversibility. Okay. Great. Good. There is a very important thing. When we try to do a complicated circuit, it is very important to think about how we build such a circuit out of simple universal ones. So I'm gonna have a single qubit gate and a multiple qubit gate. Like if I wanna design a complicated circuit, I would like to do it like the Lego. You basically go ahead and have pieces. عندك مجموعة من القطع عايز توصلها ببعض بحيث انك انت تبني منها هرم او تبني منها بيت او whatever. good thing انه احنا نفكر انه احنا what if we have at the end one single qubit gate, so one single qubit gate زائد one specific double qubit gate, and use them all the way to build all this structure, all this big building. يعني عايز بس هو نوع واحد من السنجل كيوبيت جيت، واحد دبل كيوبيت جيت، واجمعهم مع بعض علشان ابني البناء الكبير ده. ف this is what we do actually، ان احنا بنستخدم السي نوت as our building unit. You can use the NOT gate as your building unit as well for the single qubit, and C naught for the double qubit. So if you combine them, you can create any kind of gate, higher level of gate, after combining them in many different ways. Okay. I'm not going to talk about measuring in another computational basis. Probably that's not very important here, at least for now. Now, you can now do something like how we can do a quantum circuit. Okay. Now, I can do a quantum circuit. As you can see, remember, this is the notation or the symbol that we used here for the C naught. So this is how it looks like. So basically, if you look here, okay, at this here, this is how the controlled or the C naught gate looks like, and we saw how it works. Okay, now we can start building quantum circuits, which has, for instance, 3 quantum gates, okay? And we can look at it this way. So it's like I have here, if you guys look at this, I have here a C naught and another reversed C naught and another one here, okay? So when we do this, so as I said, you can use your C naught gate, which acts on 2 qubits. You can use it as your unit. Building a higher gate can be done by connecting a group of C naught gates together. Here, this is exactly what happens when you do that. You have a C naught and C naught and C naught, as you can see, arranged in this way. And you start from here, and basically it's gonna flip. So you start here with A and B. I'm gonna write this here. You start with A and B, and after applying those 3 gates, you end up with B and A at the other side. And this is why they call that the swap gate, swapping. So this is a swap gate, where you start with A and B, but you end up with B and A here, okay? So this is an example of how we can build basically a circuit, and that circuit is made of just the same units, which is the C naught, okay? So that's what we have for a quantum circuit, for instance. Of course, you can do more complicated circuits. يعني ممكن نصمم circuits تعمل jobs تانية، بس دي واحدة من الحاجات اللي احنا بنحتاجها في الكوانتم computing to swap 2 gates state. ننقل ده مكان ده. Okay, so that's what we did here. Okay. Yeah, of course, I think probably if you guys, as they said, you guys saw that already before, you know, wires are not doing anything. Just يعني لما نبص على wires هنا, they do nothing but basically transferring the qubit as it is. But then this is the gate itself. So wires are not really doing anything. The black lines here are doing nothing. Okay. Very good. Great. So yeah. Okay. In a very similar way, so we saw the gates that we found before, and basically we saw that we can do the control U gate, which is an extension of the C naught. So we saw basically, okay, we saw before the C naught gate, which takes one control and one target. And basically, based on the control value, you are giving some instructions for your control here, okay? And you end up, you end up doing something like, you say, okay, flip if you have the control and the target all what it does is X. So basically here is 0. If this is 0, it's okay. If this is 0, the control is 0, nothing is going to happen to the target. So 0 is going to end up with 0. But if you have here, so it's like, okay, so this is your control and this is your target, basically. And what you are going to get, okay, so this is like my A, B, and this is the outcome, A prime, B prime. So basically, as we said, if you feed it, the control is 0, you get a target 0. If the control is 0 and this is 1, you end up doing nothing, because if the control is 0, it says do nothing. And then you get here the 0 and here 1. But if the control is 1, it's going to flip. So you have here 0. It's going to give you at the end here 1. And if the control is 1 and this is 1, so the control stays the same 1, but this is going to flip, and so on. Now, so what the control does, it gives instruction for the other side here to do an operation. We can make that actually happen instead of the C naught. Okay, I'm gonna do a CU gate, where basically now here you have either 0 or 1 entered into this side, okay, at the control. And you have here several qubits, so n qubits. And you are giving them to a gate which is gonna perform what you wish. If you have 0, it says to this U, don't do anything. If you are putting here 1, it says do your job. And this job could be anything that you are gonna do on the n qubits. So you end up basically doing what we call it the CU gate, okay? And again, this U could be anything. It could be doing any operations on the n qubits that you are feeding it with. So this is the controlled U gate. Okay. One of the very important things, of course, that we do is doing the measurement. If you feed, okay, if you have a measurement apparatus here, okay, and you basically did some operation. So imagine that you have here gates and you started with some initial psi. So I'm going to call it psi 0, for instance. You did some gates. So those were quantum gates. But at the end of the day, I have to do something. I have to measure something. So I'm going to apply a measurement process to psi to end up with some value that I'm looking for. So that is what we call it, the measurement process. And it's going to give me a classical value. So up to this point, we had quantum information. Okay, because all what we have done here is we started with quantum information, we processed it, and we ended up with some state for the system that we are working on. But once we make a measurement, we are now in the phase of having classical. بقى عندنا دلوقتي classical information. So we end up having classical information because we did a measurement. If you, for instance, that's an example. If, for instance, I have a psi that is alpha 0 plus beta 1. If this is the case, I'm going to take this and make a measurement. So this is the symbol for a measurement. We use it in quantum circuits. If you make a measurement now on this psi, I'm going to get either I'm going to get either 0 or 1, as we know. Once I made the measurement and I made the wave function or the state of the qubit collapse, I have now a classical piece of information. I know that for sure the system is in either 0 or 1. And we know that the probability to get this, as we said before, is alpha squared. And the probability here is beta squared, as we know. So we made a measurement. So now we have a classical information. We usually represent that using those two parallel lines, as you can see here. So basically, we end up having these two parallel lines saying that now I made a measurement, I have a value that came out, and this is classical now. Good. One of the things that we would like to talk about is, can we do copying of a qubit? If you have a qubit, can you have a copy of it? Okay. In classical physics or in classical computing, you can have basically such a case where you can start with X, you can feed some gate, classical gate with X, for instance, and 0, and you do an operation which is gonna give you X back, and here you are gonna get another X. So if you design this, if you make a truth table for this gate, where the first bit is X and the second bit is 0, and basically this is like my X and this is my Y, I'm gonna apply X plus Y here, and that's gonna give me the X back. So I now made another copy of X. So that is possible classically. Now, the question is, can we make a copy of a qubit like what we did with the classical bit? So the classical bit, we can make a copy of it, cloning it. نعمل منها نسخة أخرى يعني. هل ممكن نعمل يعني خد بالك نسخة أخرى معناها إنه أنا I still get X and another copy of it. Can we do that in the quantum case? Can we copy a qubit? So if you start with a qubit, for instance, in the 0 and 1 with a combination A and B, I don't know what is the A and B because it's like an unknown state. So I'm feeding my circuit with an unknown state. It's a combination of 0 and 1. Now, the question is, if you basically put here a 0, like what we did in classical case, if I put the qubit, second qubit in the 0 state, what am I gonna get at the other side? I'm gonna get this. If you just apply the rules for the C0, I'm gonna get basically this here at the other side. I'm gonna get a combination of 0, 0 and 1, 1. Okay? And that's what you can look at here also. you have the first qubit as A0 plus B1 times 0. And you have here A00 plus B10. Have we copied psi this way? Did we create two psi's? I mean, is it psi times psi? Like, you know, if you want to do, okay, let me show that here. To get psi, it means I have something like that. I'm gonna have A0 plus B1 times A0 plus B1. That's what it means. So I should get something like, you know, so I'm gonna get basically A times A is like A squared 0, 0 plus, you know, AB 0, 1, right? And then here BA 1, 0 plus B squared 1, 1. So what we have is 0, 0, 0, 1, 1. But we didn't get that. This is what we got. So applying here the C naught, what happened is we did not actually get all those states. We got only, as you can see, okay, it's like multiplying this by this. And this is what we got. So in fact, I'm getting now this term, okay? I'm getting now this term, and I'm getting now basically this term here. Okay, I mean, of course, with different coefficients, but this is what we are getting, this one here. So we couldn't really do any cloning of it. The only exception is if you, in fact, make one of those two zeros. So let me show you here. If you look at this as psi, as I said, times psi, like getting two psi's output, this is what we should get at the end, okay? But the thing is, you have to have, okay, AB equals 0, okay? And that's what we got, actually. So this was 0, and this was 0. So we cannot actually make a copy of any unknown quantum state. We cannot. There is impossible. It's impossible to get a way to make a copy of, I mean, you cannot start, again, I'm just gonna explain that to be clear. You cannot start with something like that and you create basically two copies of it. Like here, A is 0 plus B1 and A is 0 plus B1. You cannot end up having two copies of your state. The only way is that if you actually start here, the only way, if you actually remove one of those guys, like put B0, then A0 can be, the 0 state can be copied. Okay, you can get two copies of the 0. Or if you put A0 and you keep B as 1, then you can make a copy of 1, because this is allowed. But the thing is, this means I am not copying a qubit state. I'm copying. So it's like if you get, for instance, 0, okay, you can have two zeros at the end. You can make a copy of, so you have here, okay, as you see here, I'm going to put a 0 here, but the one I'm copying is 0. So if you have 0 and 0, actually, I can end up with 0 and 0 from this gate. Okay, I can end up with two zeros. If I have 1 and 0 here, okay, I can end up with 1 and 1. That's allowed. But in fact, if you look at it, so you cannot do that. This is not allowed. You cannot do it. You cannot copy or make a cloning of a qubit state and create another one exactly the same. But if you start with a classical one, because actually if your qubit is just one, this is like a classical piece of information. You are not in a linear combination. You don't have the probability. You have a classical bit. So using this gate, actually, I can make a copy of a classical piece of information. If you have one, you can create one and one. That's okay. If you have zero here, if you have a zero entering here, you can create a 0 and 0. But you cannot have the two things, a combination of the two things. So we cannot clone a qubit. And this is what we call it no cloning theorem. And this is actually very important in security, the security theory for quantum computing, that if you start with a qubit, no one in the middle can spy on it and create a copy of it. So that's actually a big advantage in quantum computing and quantum information processing and quantum teleportation, because basically no one can. So think about this. You are sending, for instance, sending a piece of information from this place to this place. You are making quantum teleportation and you are sending a qubit state. So you are sending A, okay, okay, 0 plus B, okay, 1 from here to here. If someone in the middle, so this is unknown. I mean, for the spy, for the spying guy, this is an unknown state. So if he has a way to make an operation on it and make a copy of it, this means he can actually manipulate it. He can play with it. He can get the kind of information you are sending out. But because cloning is not possible in quantum circuits, you cannot create any copy of any state that you are sending out to another one, because once someone works on it, he's gonna destroy the information that it carries. So it's gonna change the state. Those are kind of examples of other circuits that you can basically do. For instance, we have very important states, qubit states, 2 qubit states, that we call them the Bell states. They are maximally, they have a property that we call it maximally entangled states. And here, this circuit here, for instance, is designed to create the Bell states. So if you look at this circuit here, okay, so if you look at this circuit here, you are giving this circuit X and Y, and then you apply Hadamard gate and then NOT gate. And you get at the end, so you start with X and Y, giving them certain values, and you are going to create at the end one of the Bell states. For instance, this table is giving us all the possibilities. If you put X as 0 and Y as 0, you can end up with this Bell state. We call it beta 0, 0. And if you feed it with 0, 1, you get B0, 1. If you feed it with 1, 0, you get 1, 0. If you feed it with 1, 1, you get beta 1, 1, which looks like that. It's a linear combination. One of the interesting things about this is that X and Y are just classical pieces of information, because you are feeding actually the circuit with 0, 1, or 1, 0, or 1, 1. So you are in fact not feeding them with, any linear combinations of zeros and ones. But because of the Hadamard, and we saw that before, the Hadamard gate takes 0 and convert it into 0 plus 1. And if it takes 1, it's going to convert it to 0 minus 1. So in fact, that's what its job. It takes a classical piece, but it converts into a linear combination. And you end up with all those build states here, as you can see here. Okay, so those are, this is a very important and famous gate, as you can see here. So, you know, we can write a general form for the state this way. Okay, everyone. So this is, yeah, I think we are running out of time. I wanted so much to do quantum teleportation, but it's gonna take some time. And actually, I have to stop here for today. Hopefully, in the future, we can have an opportunity to do more of this. But I have some other things that I have to go to, meetings. So I'm gonna stop here and get a few questions if you guys have a few questions.
دكتور لو حضرتك وقت
ايوه اتفضلي.
لو حضرتك عندك وقت ممكن نكمل ربع ساعة كمان.
المشكلة ان انا I have a meeting في الجامعة، فللأسف الشديد يعني خلال مثلا 15 minutes I have to move. فيعني ممكن in the future we can arrange another lecture about quantum teleportation and how we do it and about انا يعني كان عندي احلام عريضة ان احنا هنعمل حاجات كتير، نعمل جوسة you know algorithm ونعمل الجوريزمات وحاجات، بس يعني الوقت الحقيقة ضيق جدا. So maybe in the future we can arrange something even beyond the scope. يعني في تبع ممكن نعمل حاجة تبع السوسايتي في تايم تاني، مفيش مشكلة يعني. Okay,
خلينا ننظم سيمينارات لحضرتك معاهم.
ان شاء الله.
تمام. اوكي
تمام.
طيب خلينا
معلش
نبدا.
انا بعتذر انه الوقت، معلش النهارده انا عندي ميتينجز كتيره في الجامعه ولازم اتحرك الحقيقه، يعني اروح اعملهم يعني. سوري I'm very sorry يعني يا جماعه. اتفضلي.
خلينا بس ناخد بروفيل الاسئله بس.
Thank you Professor Jahad. Thank you for this interesting lecture. Thank you. ان شاء الله يعني هننظم خلال الفتره الجايه السيمينارات الشهريه اللي احنا بنعملها وندلف اكتر ان شاء الله معاهم.
ان شاء الله.
ان شاء الله. Thank you Professor Jahad.
If you guys have a questions, I can take a few questions.
خلينا ناخد اسئله يا دكتور.
Yeah, sure. اتفضلي.
لا تعالى هنا.
صباح الخير يا بروفيسور، ازي حضرتك؟
يا اهلا وسهلا.
اهلا بحضرتك. انا الدكتور رمضان بكير.
يا اهلا دكتور.
اهلا بحضرتك. الحمد لله. بقول لحضرتك ايه الكوميونيتيز اللي ممكن نستفيد بيها في الكوانتم؟ يعني ممكن ايه الحاجات اللي بتقدم خدمات للناس وكده في الليرنينج والكلام ده؟ يعني لو حضرتك تعرف يا ريت تبابلش لنا حاجه شبه كده.
يعني ما فهمتش السؤال قوي. تاني.
يعني حضرتك مثلا ايه الجروبس اللي ممكن تفيدنا لو احنا عايزين نتعلم اكتر عن الكوانتم يعني وكده؟ ممكن لو في جروبس او بتعمل ليرنينج الكلام ده يعني.
تمام. اوكي. يعني I will talk to دكتور زيدان and if I have some suggestions I'm gonna send it ان شاء الله. يعني بس هو مفروض كل الشركات الكبيرة اللي شغالة على الكوانتم كومبيوتينج هم عندهم منصات خاصة بيهم، تقدر تدخل تقرا الحاجات بتاعتهم، وتقدر حتى تكريت ان اكاونت، وتقدر تعمل برامج صغيرة تعمل بيها يعني quantum circuits. You can make a program to do a quantum circuit where you بتبتدي تفيد البرنامج، يعني feed it، يعني تغذيه بقيم ويعمل لك الحسابات ويطلع لك from the other side the values that you should get. ففي حاجات من دي كتير. جوجل، اي بي ام، they have their own websites ومنصاتهم where you can go even create an account and do calculations using their quantum computers, quantum processors يعني اللي هم حاطينهم يعني.
تمام. في حد كمان عايز يسأل؟ اتفضل.
اتفضل.
I want to ask about why we are not interested or focusing on the coefficient when we copying a quantum qubit. For example, in 0, we got just 0, 0. Where is the a square or the coefficient of 0?
Are you talking about here, for instance, or what?
No, before.
Is it this?
Slide
Okay.
of copy.
Copying لما هنا.
أيوة.
Are you talking about this one? Yeah. بتتكلمي على maybe you are talking about this one here, or what?
If
Or
I
here?
want to copy the next slide, if I want to copy a 0 qubit,
This
the
one
next
here?
slide. Yes.
This one. Okay. Yeah. قولي لي. أيوة.
If I have a 0 qubit and I want to copy it, you just explain it. It goes to 0, 0. But where is the a?
لا هنا if you are talking about this one, for instance, here, right? This one, right? مش كده؟ Okay.
أيوة.
What we are saying is the following. خلي بالك أنا بقول إيه، لو أنا عندي الكوانتم جيت هنا وأنا مدخل لها ده عشان عايز أعمل كوبينج هنا. شوفي دي كلاسيكال، الكلاسيكال جيت أنت بتديها إكس وزيرو وبتطلع لك إكس وإكس الناحية التانية. أوكي. المقابل بتاعها انه احنا نصمم جيت مشابهه اللي هي السي نوت جيت. اوكي. او يعني this gate here. سوري اللي فيها الاكس اور. سوري. فانت if you do this اوكي هنا you end up يعني اذا دخلتي للسيركت دي، اذا دخلت لها ايه يعني دي كيوبت مجهوله، ما حدش عارف الاي والبي بتوعها بكام. انا كاني مدي الجيت دي كيوبت مجهوله وبقول لها create copies of it copy of it. فلازم تديني نفس الكيوبت باك وتديني كوبي تانية منها. في الحقيقه ده ما بيحصلش. اذا انت شفتي اللي احنا مطلعينه هنا، انت بينتهي بيك الامر انه انت بيطلع لك ده الحاجه اللي هنا دي. شايفه ده اللي هو A00 B 11. So you didn't get two copies في الحقيقه، لانه two copies have to look like this. انه يطلع لي ده وده كانه عندي ابساي وابساي كانهم يعني this is what I have to get out from the other side. اللي ممكن يحصل، الحاله الوحيده اللي ممكن نعمل فيها كوبينج والموضوع يشتغل كويس، لو انا دخلت زيرو، لو انا دخلت هنا زيرو بس من غير يعني الاي كانها بواحد والبي كانه الاي بواحد والبي بصفر، ساعتها هتطلع لي الناحيه الثانيه فورا زيرو زيرو. ولو انا دخلت هنا واحد مع الزيرو ده هتقلب وتبقى واحد وواحد. فانا في الحقيقه اللي هيحصل انه انا لو دخلت يعني let me write that down here. لو انا دخلت okay I'm just changing the colors. يعني لو دخلت في البتاعه دي كده اوكي لو انا دخلت لك هنا زيرو مثلا، معناها ان الاي بواحد والبي بصفر. زيرو معناها اي بواحد وبي بصفر. فانا مدخل كلاسيكال بيس اوف انفورميشن هي في ستيت معينه مفيش probability، وهنا في زيرو هنتهي باني عندي زيرو زيرو. لو دخلت هنا 1 هنتهي هنا بان عندي 1، وهنا كمان هيقلب يبقى 1. ف الحاله الوحيده ممكن تعملي لها كلوننج انه يكون عندك زيرو فيطلع لي الناحيه الثانيه زيرو زيرو، او يكون عندي في الناحيه دي 1 فيطلع لي 1 و1. فانا في الحقيقه هنا ما بعملش كوبينج لكيوبت ستيت لانها ما فيهاش الاي والبي، هي في الحقيقه يا صفر يا 1. فانا دي كانها كلاسيكال بت او سوري كلاسيكال بيس اوف انفورميشن، لانها صفر انا عارف انا مدخل ايه بالظبط. هو صفر هيطلع لي الناحيه الثانيه صفر وصفر. لو مدخل واحد يبقى واحد واحد يطلع لي واحد وواحد الناحيه الثانيه. فانا I ended up عامل كلوننج لكلاسيكال بت مش لكوانتم بت. يعني اعرف اعمل نسخه من كلاسيكال بت، بس ما اقدرش اعمل نسخه من الستيت بتاعت كوانتم بت. ده اللي حصل، وده no cloning. You cannot in quantum circuits you cannot produce a copy or make a cloning of a state of a qubit. اوكي
Okay, thank you.
ده اللي كان مقصود. بقى احنا still نقدر نعمل cloning لكلاسيكال piece of information بس مش لكوانتم ستيت، وده advantage في الكوانتم كومبيوتنج في الحقيقة. اوكي
تمام يا دكتور، في حد كمان عايز يسأل، اتفضل.
اتفضل.
دكتور احنا كنا قايلين ان الكوانتم كمبيوتر عنده القدره ان هو يهاك كلاسيكال كمبيوتر عادي. جميل. طيب كنا عايزين نأسكت حاجه هنا. لو افترضنا مثلا ان احنا بنحاول نهاك حاجه زي فيسبوك، هي سيرفر موجود، هو كلاسيكال كمبيوتر موجود، وانا بحاول ان انا بروت فورس على الباسورد بتاعه، فبالتالي انا بستنى الريسبونس اللي راجع لي من كلاسيكال كمبيوتر. فهل ده اصلا ابليكابل ان احنا نقدر نعمل ده بكوانتم كمبيوتر؟ وهل هو لو ابليكابل ممكن يتعمل؟
خد بالك الطريقة اللي بيتم بيها عمل يعني انت بتعمل ايه؟ هو انت الكتير قوي من السكيورتي ميجرز اللي بيعملوها كتير قوي من السكيورتي ميجرز اللي بيعملوها في الكلاسيكال سيستمز ان هو بيبقى عنده رقم كبير جدا. يعني مثلا خليني اقول لك، عندك رقم كبير جدا كويس، مثلا 128 ديجيت كويس، وانت عشان تفك الكودينج اللي هم عاملينه لازم تعرف البرايمري نمبرز بتاعت رقم مكتوب ب 128 ديجيت. يعني تكتب انه ده هو عبارة عن 2 مضروبة في 3 في مش عارف ايه كده، عشان تفككه لانه يبقى البرايمري نمبرز بتاعته. عشان لو انت عندك رقم عنده 128 ديجيت، عشان تفككه وتفك، يعني هو عاملين ده علشان محدش يعرف يفك التشفير اللي عندهم. الكوانتم كمبيوتر، الفكره بتاعت الكوانتم كمبيوتر ان هو ممكن ياخد such a number. يعني انا حتى لو اديتك النمبر ده، انا بنك وعندي 128 ديجيت نمبر، وقلت لك خد ده الرقم بتاعي اللي انا عامل بيه السكيورتي بتاعته، انت مش هتعرف تعمل البرايمري نمبرز بتاعته، لانه محتاج سوبر كمبيوتر يشتغل مثلا آلاف السنين عشان تعرف تفككه. الفكره في الكوانتم كمبيوتر انه يقدر يعمل prime factorization in few minutes. يعني ممكن ياخد الرقم ده ويطلع لك ده واحد من ال very famous algorithms اللي موجوده في quantum computing الناجحه، انك اقدر اعمل factorization للنمبر، لاي نمبر، للبرايم نمبرز بتاعته، وبالتالي انا اقدر اروح اعمل ده عليهم. فاهم ازاي؟ اقدر اروح واعرف الرقم بتاعهم السري. هم ممكن يقولوا لك خد اهو الرقم اهو، بس ورينا هتطلع البرايم نمبرز بتاعته ازاي. Do you get that? So
يعني
this is how it works. اتفضل.
طيب يعني يا دكتور ما اقدرش ان انا مثلا ادخل، يعني انا كده المفروض ان انا يبقى معايا الناتج النهائي. مثلا لو احنا بنتكلم على ار اس اي اللي هو اللي حضرتك شرحه ده قريب من الار اس اي، ان انا كده معايا رقم حاصل ضرب رقمين برايمز ومعايا الناتج النهائي، فهو بيجرب على كل الارقام لحد ما يوصل للرقم اللي هو الاساسي اللي حصل لهم ضرب، فنتج لي عن ذلك اللي هو الرقم الكبير اللي انا دخلته للكمبيوتر هو جرب.
ايوه
طب حلو قوي.
بالظبط، هو بياخد
وانا
الرقم الكبير، هو عنده الرقم الكبير وبيفك الكوانتم بروسيسور هياخده ويفككه لك الى ارقام صغيره.
لكن
فاهمني؟
فهمت. لكن انا ما اقدرش مثلا ان انا اهاك كلاسيكال سيستم انا اصلا ما اعرفش عنه اي حاجه غير ان هو فيه باسورد بس.
انت في الاخر انت هتهاك بالطريقه الكلاسيكيه وتجيب الرقم اللي هم مخبيينه وتعمل له باستخدام الكوانتم بروسيسور، هتعمل له فاكتورايزيشن. اوكي، بس فاول ما تعمل ده هترجع تاني بطريقه كلاسيكيه تدخل على السيستم بتاعهم، بقيت انت عارف تفك الكود بتاعهم ازاي فهتدخل. يعني الكوانتم كمبيوتر مهمته مش انه هو نفسه يهاك، هو هياخد يعمل لك بروسيس على سكيورتي كودز عندهم، انت هتجيبها وتديها له وهو يحلها لك ويقول لك ادي يا سيدي البرايم نمبرز اهي، روح بقى خدها اعمل بيها اللي انت عايزه. دي جيت ذات؟
احنا معانا
اوكي احنا يعني
فهمت؟
السؤال كمان، هي الالجوريثم بتعمل كده، هي شورز الجوريثم تقريبا، مش صح؟
ايوه مظبوط. في عندك يعني الكوانتم كومبيوتنج من 1980s كان موجود والناس بتفكر فيه، وبعدين مات ليه؟ لانه الناس ما كانتش عارفه تعمل بيه ايه، لغايه ما طلع الدايتش الجوريزم والشور الجوريزم. فابتدوا يقولوا لو عندك تقدر تعمل سيرش على داتابيس ضخمه جدا، رايت، وتطلع منها المعلومات اللي انت عايزها in no time. مش كده؟
ايوه جميل.
وتقدر تعمل فاكتورايزيشن لاي رقم كبير. قبل الشور والدويتش الجوريزمز الناس كانت شايفه انه الكوانتم كومبيوتنج ملوش اي معنى، لان احنا ما عندناش الجوريزمز ولا بروجرامز ممكن تحل لنا اي مشاكل حقيقيه. كويس. ف ف ف ف this is why it became now very important. وليه الحكومات بقت خايفه من كوانتم كومبيوتنج في كل العالم؟ يعني انه الناس اللي هتبقى عندها quantum computers is gonna hack everyone else. هتعمل يعني فك للشفرات بتاع الجميع، وبالتالي everyone is worried about his stuff يعني right.
شكرا جدا لحضرتك يا دكتور، ربنا يخليك.
يا اهلا بيك.
في سؤال كمان يا دكتور صادق.
This is last question علشان I have to go معلش.
لو عايز تمشي دكتور جهاد ماشي، انا ممكن اسال السؤال وبعد كده
لا no you can ask وبعدين اتفضل. يا اهلا وسهلا.
لو بالنسبه للكمبيوتر الكمي او الكمبيوتر اللي هو يعني في مشاكل ده، يعني هو المشكله مش في سوبر بوزيشن بتاع ان احنا ما نقدرش نتحكم في المعلومات دي كلها، فما نقدرش نعمل كمبيوتر كمي، ولا ده جزء نظري؟ فهل في مشاكل تانية في التكنيك؟
يعني هو اكبر مشكله بتقابل الكوانتم كمبيوترز انه الكوانتم سيستمز نفسها فراجل جدا، يعني هشه جدا. يعني انت ما بتخزن معلومات، اما بتخزن معلومات على السيستم، المعلومات دي بسبب الانفايرمنت المحيط بيه اللي هي الايرور كوركشنز بقى اللي الناس شغاله عليها دلوقتي، بيحصل ايرورز. الايرورز بتحصل بسبب النويز. انت مثلا انت بتتكلم على انك عامل اتوم مثلا ومخزن عليها معلومات. الاتوم دي انت عايز تحتفظ بالمعلومات عليها وتعمل عليها جيتس تغير لك المعلومات اللي عليها. الالكترون مثلا كان تحت، عايز تطلعه فوق او تحطه في لينير كومبينيشن. وبس هو انت لازم تحافظ على اللي انت بتعمله ده، ما فيش حاجه من بره تيجي تلخبطه. النويز المحيطه، الاتوم دي اللي انت بتشتغل عليها هي محاطه بملايين الاتومز في السيستم اللي بناها. و sometimes you have an interaction between الاتومز، between الكيوبات اللي انت مخلقها والستراكشر اللي حواليها. You have to make a clean environment. You have to make error corrections. لما تحصل error تقدر تصلحها. الحاجات دي كلها حاجات هامة جدا لازم نشتغل عليها علشان نقدر نعمل quantum computing. الدي coherence اللي هم فقدان السوبربوزيشن والفيز relation between the 0 and 1. كل الحاجات دي مشاكل موجودة. في حاجة تانية احنا بنشتغل عليها في الريسيرش بتاعنا اللي هي entanglement sudden death، اللي هو الموت المفاجئ للentanglement between the qubits because of the environment surrounding them. So there are so many problems. بس the good news ان there are so many groups working in the world، وكل جروب شغاله على سيستم. يعني في ناس بتشتغل بالكوانتم دوتس، في ناس بتشتغل بالسوبر كوندكتورز، في ناس بتشتغل بالفوتونز، بيحاولوا يعملوا كومبيوتيشن او كوانتم كومبيوتنجز بالفوتونز، بالترابد ايونز. وكل سيستم عنده مميزات وعنده عيوب، والناس بتحاول تصلح المشاكل الموجوده وتعمل ميتيجيشن زي ما كان دكتور زيدان بيقول. نعمل كده ايه، معالجه وتصحيح للحاجات. ف this is what they are doing يعني. اوكي يا استاذنا. تمام. انا شاكر ليكم جدا.
بس يعني انا بكلمك على الخاص دكتور.
شكرا
ان شاء الله ان شاء الله. اشكركم. انا معلش لازم امشي. شاكر جدا لانتباهكم، وهبعت الحاجات ان شاء الله للناس تحطها على الويب سايت اللي احنا عملناه، ونلتقي قريبا ان شاء الله. اشكركم جدا. السلام عليكم. مع السلامه.